Alright guys, welcome back here. In this video we're going to talk about lesson 4.2. In this lesson we're going to go over how to find the second derivative of a given function and discuss the concept of the geometric interpretation of the second derivative. So goal is try and figure out what does the second derivative tell us about their first derivative and also the function itself as well. Okay, so that's the ultimate goal there. Before we get to that part, I want to just introduce briefly the notation of the second derivative and then go over a few examples how to find the second derivative of a given function. So let's start with notation here. Okay, so notation. Okay, so if y is equal to f of x, that's the given function, then the second derivative of f of x is denoted by f double prime of x. And to get f double prime of x as the second derivative of the function, we take the derivative of the first derivative, so just d dx of the f prime of x. Or we can denote that as y double prime, the second slash on top of the y prime, show that we're looking at second derivative of the function. So sometimes you see a notation with this as well. D squared y over dx squared, and that just means taking the derivative of the function of y respect to x twice. That function is not as being used as the y double prime here. So now we got the notation situated. Let's look at it, just example. How would we find the second derivative of a given function? So let's look at example. Okay, so find f double prime. Okay. All right, part A, let's look at f of x as x squared, right? So if it's x squared as a given function, f prime is going to be 2x, therefore f double prime is going to be just 2, okay? So pretty simple there. Let's look at another one, given g function as square root of x. So for this one, we might want to rewrite this as a rational exponent form for x to the 1/2 power. So that way we can just go ahead and take the first derivative using the power rule. We're looking at 1/2 x to negative 1/2, right? So let's move on to the second derivative. So that's g double prime of x. Using the power rule again, we get negative 1/4 x negative 1/2 minus 1. So we're looking at negative 1/4 x to the negative 3/4. Okay, so that's the second derivative of the g function square root of x. Let's do another one. Let's combine several terms and apply the power rule several times there. So suppose we have ax to the 7 plus 19x to the 6 minus 12x squared plus 2, for example. All right. Applying the power rule to find the first derivative, we're looking at 56x to the 6 plus 19 times 6. I don't even know what that is. 19 times 6, 54, 11, 114 x to the 5th minus 24x. And the derivative of 2 is going to be 0. Let's move on and find the second derivative, f double prime of x. What is 56 times 6 here? I don't know. 6, 3, 33, 336x to the 5th. Plus 0 to 7, 570 x to the 4th minus 24, right? Pretty simple there. Just find the second derivative using the power rule. All right. So nothing really changed in terms of what we've been doing up to this point, how to find the derivative of a given function. So what we're about to get into is introducing the concept of second derivative in terms of the graph, in terms of geometric interpretation. What exactly is going on? How do we visualize what the second derivative is in terms of picture and make sense of it? We do know this from the previous lesson here. We know that if this is from 4.1, so less than 4.1, if f prime of x is greater than 0, then the given function is increasing over an open interval. Okay, and if f prime of x is less than 0, and then f of x is decreasing. So we do know that from the previous lesson 4.1. The relationship between the first derivative and the graph, or f of x values. In this lesson, we relate f double prime to f of x to its graph. And that's the goal there, okay? So I'm going to go ahead and go down here. I'm gonna consider an example. Let's consider an example that I've already typed up here. Let's look at an example of this here. Suppose we're given two functions. All right. So suppose we're given these two functions, f of x and g of x, both defined on an open interval 0 to infinity. So I'm going to go ahead and graph these two functions for us here. Okay. So suppose we have f of x graph that looks like this. That's x squared, so we're looking at just increasing. So this is x. And then this function here is f of x. Okay. Now let's draw the graph of square root of x. Square root of x. So we're looking at that. You can just do this on Desmo to verify these are the correct graph here. And then let's label this g of x. Okay. So what do we know about these two functions? Both of these functions are increasing functions. Both are increasing functions on an interval from 0 to infinity. So let's do that. So we do know that f and g are increasing functions on interval 0 to positive infinity. What do we mean by that? Well, let's see here. Let's say we pick a point there. Here's x, here's y. So we go up to here. Here's x, here's y. As x increases, y also increases as well. Same thing here. We pick a point over there. Here's the x and y position. And let's move to the next point. Notice that as x go up, y's also go up as well. So both are increasing functions. But what's different between these two functions? Notice that the way the graph is portrayed slightly different. Both are increasing, but increase slightly different direction there. So how do we describe the difference between these two graphs? We're going to use the first derivative. Okay, so let's use the first derivative to describe what type of increasing function we have there. So suppose we draw the slope of tangent line there and there and there. So this is f prime of x. And then now look at g prime of x. All right, so what do we notice here? So the slope of tangent line are increasing, a positive first, but also increasing. So as we increase the x value, the slope of tangent line gets steeper and steeper, whereas here, the slope of tangent lines are getting less steep and less steep as x increases. So we call this behavior here, we say that f prime of x, okay, a positive, but also positive in the increasing directions. Okay, here the g prime of x, so also positive, but the slopes are decreasing. Slope of tangent lines are decreasing. So g prime of x is decreasing. Okay, so we can go ahead and say that. We say that f prime of x is increasing, but g prime of x is decreasing. Okay. So although both functions themselves, both graphs portray the function value are decreasing, however, they have different rate of increasing. So the f functions is positive increasing rate, and then g of x is the negative rate increasing, meaning as x value increases, the g values of x, the function value is increasing, but increasing at a slower rate as compared to f of x function, right? So we can say this as f has a faster increasing rate than g. Okay, all right. Okay, so what do we have so far here? We're given two functions. describe that they are both increasing. However, the derivative is slightly different. One has a positive derivative and the other one has a negative derivative, and we can verify that up here. I think we've done this example already. So you see how f of x here, x squared, this one has a positive derivative. This one here also have a positive derivative, but has a different rate of derivative. And even still, so how do we really show the difference between these two functions here? Although the derivatives themselves are both positive, but then one is increasing, one is decreasing. What we're going to do next is we're going to bring in the second derivative and tie that to the graph itself, okay? So if we observe the formulas up here, we say that one is a positive, one is a negative second derivative. So we say in this case here, this is a positive second derivative. This is a negative function there. So we can say that f has f double prime. So let's say f double prime of x is positive for all x. For all x on the interval 0 to infinity. However, g double prime is a negative function, so it's a negative. G double prime is negative for all x on 0 to infinity. So I'm gonna go ahead and end the video here, but what we're gonna do next video is tie these two things together. Okay, how does the second derivative being positive relate to the first derivative and to the graph itself? So that's going to be the next video. Okay, so I'm going to go ahead and end this video here.